Hello there, math fans. Going to talk about the vector sum concept. I have been telling this story for years. I've been teaching at the University of Washington for 20 years of remembering when I was a kid in gym class having a scooter like this. And everyone would get on them. You'd push yourselves around the room. You did all sorts of activities, played games. I remember it fondly. um, I was searching for images and I saw these images, which sort of bothered me that this is what people have now because this has a way to protect your hands. I'm going to tell you how this pertains to vectors because I think it hits at the heart of how I think about vector sums. A lot of students think about these things so mechanically without understanding maybe why they matter so much. And I'm certain that this is a fairly unique perspective. But I remember always getting your hands smashed. We used to play on these, so it's a fun and painful memory. In a moment, I will pull myself around the wagon while Harry the Husky and Butch the Cougar the mascots will pull me around in a little bit. I'll have them pull me different ways because I think that's how I think about vectors. But let's do the classic definition of vector sum. So let's say you have this vector 3, 1, and I've drawn it here. For some reason, I drew it with its tail in some random place, but over 3, up 1. Let's say then we have another vector. Let's have it go to the left. Let's have it be -1, 5. Now, if you just draw -1, 5, it might look like this if you drew it from the origin. And I should make it more to scale at -1, 5. And this probably none of this is to scale. But remember, you're free to move them. We just think about them as changes is another way to say it. If you put the tail here, you're going to have this 1 3. I was just trying to draw it a little shorter. Okay, so we have these two vectors, and we want to add them. Now, the reason we want to add them, and the definition we're about to do, is because of that wagon pulling. Not wagon, scooter pulling. The definition itself is super easy. And so I think we get too hung up on other things. So let's just do the definition before we talk about interpretation. You add component-wise. So the definition is just to add 3 to -1, and then add 1 to 5, and it's quick. It's just going to be 2, 6. That's it. So there's not really a lot going on here. It's fairly easy to execute. Oftentimes in practice, the hard part is getting the initial two vectors. You usually spend more energy in practice figuring these out, because once you have them, the adding piece is easier. But someone at some point was like, well, let's try to visualize them. And I know when I was a student, what I learned was this head to tail rule. Basically, you take the head of this one of the vectors, it doesn't matter which one, you take the tail of the other one, you move it over, and you draw it. So you draw this little 3, 1. And again, I did a bad job of my scaling, but who cares? So we're going to draw this little 3, 1. And the point you're at here, if you drew it from the origin, is this point 2, 6. If you draw it as a vector from the origin, so meaning from the original tail to the final head, that's your sum vector. Now again, I don't know that that tells you very much about what's going on, and so that's why I always talk about this scooter thing. Sometimes you see it explained another way, which is continue to do it, but this time draw it starting with this vector, the 3, 1 vector. Draw that first, and then draw the green vector since the order doesn't matter. I didn't go far enough. Over here. There's that 3, 1. And then let's go back 1 and up 5. Oh, look, that gets us there. So that's still the head to tail rule. At some point, someone noticed that, hey, if you connect all those, what do you get? So let's connect all those. You get this thing that we call a parallelogram. Notice that the vector sum is the diagonal of the parallelogram. I don't know why I turned it. So some call this the head to tail rule, which is what I learned as a student. Some called it the parallelogram rule. I feel like none of that tells you why we do this. It is helpful for visualizing, but why? What in the heck is 2, 6? And so the story I always tell, it's really a question of forces. If you're someone who's taken physics, you've seen this. But imagine you're being pulled in 2 directions. And it doesn't have to be 2, it can be more. I mean, the other example I always think of is hanging a picture on the wall. When you hang a picture on the wall, you have like the tension in the wires. And I'm not a physicist, but you've got these tensions this way, and then you have a force going down here. And we have these 3 forces. I sometimes also talk about this as like a 3-way tug of war. If the picture is not falling to the ground, then all 3 of those forces have to add to 0. That's the same vector sum concept. But let's look at it over here. So the way I visualize a vector sum is not as a head to tail anymore, and I don't really visualize it as a parallelogram rule anymore. I visualize it as that green arrow that sticks out of both of them, which is really what it is and how we usually think about it in practice. Yeah, those visualizations are nice to get a precise thing, but really the picture in my mind when I think of adding vectors is what is the result of pulling in these 2 directions? So here we go. I've put there's the gym scooter. I've learned that you can put pictures in Desmos, which is probably for the bad. I put myself on there in a rather dumb expression, as you say, well, that's your normal expression. All right, I get it. And I've put Butch and Harry and Butch. I called the wrong one. My brother's going to be mad at me. In these various spots, and I've made it so they're going to pull. Now, if Butch pulls more strongly, you can see that my direction I'm going to go is going to be more that way. If he pulls more this way, my direction will be that way. If Harry pulls a little stronger, it's going to be this way. If they pull like complete opposite directions, my force is going to get smaller and smaller. If he has to pull back a little bit, I won't move at all if they oppose each other. So I think of the vector sum as the resultant force. You definitely can do it as a head to tail rule, but I hope that gives you a little bit of a feel. So if they both pull, my resultant force is the green arrow. And what will happen is I will start accelerating in that direction. Now, I did not actually make the animation accelerate, but I did make it animate. So I'm actually going to move at a constant speed. I didn't think about that until I was making the video. So I'm not going to accelerate, but let's make me move here. And I'm going to try to slow it down. Okay, here I go. That's the way I go as they pull. Now, are there realistic problems of, wouldn't that change how they pull once I start moving? Probably. If they pull in a different way, so that's how you should think about vector sums, because that's the main place you use them is when you're doing force. You add up all the forces. So vector sum is just adding up all of those changes. A vector represents a change. So if you add up each component, you're adding up the changes. It's not that complicated. So you don't want to get confused about the head to tail rule or the parallelogram rule. You should already have a sense of which direction that vector goes, just because you imagine pulling both those ways. And then the head to tail rule and all that other stuff just helps you get a better feel. I don't know where we want to send me. Let's say they really are trying to oppose each other. Almost straight on. It does look straight on. I think I might have a scaling thing. And then they let me go here. There I go. That's it. If they change a little bit, how they're pulling, this is what'll happen. And then I'll go that way. All right. Hope that was interesting. I think I'll stop there.